We're going to work through our lesson 8.5 questions. So I erased all the even questions, so I'm just going to try to fit all of our answers here right on the paper. I did write some things on here to help us out. If you need to write those on your paper, that would be just fine. So in the first ones, 1 to 7 the odd, it says convert to logarithmic form. We use this fact right here, that if you have a base to a power equals some number, you can change that to log form. Log base b, so the base of the logarithm, the base of the exponent is the base of the logarithm. And so for number 1, the base is 5, so we want log base 5 of 25 equals 2. Number 3, you have a negative exponent, and that's okay. It's still the same concept, so it's going to be log the base of the exponent is the base of the logarithm, so log base 3 of 1/9 equals negative 2. Number 5, log base 10 of 1,000,000 equals 6. However, we don't usually write it like that because if we have a base 10, that's considered the common log, so you don't have to write the base 10. It's an understood base 10 if nothing is written there. And the last one from this section actually shows us something fairly important. Log base 6 of 6. So the base is the same as the argument here is equal to 1. And that's going to hold true. Log base n of n will equal 1. So they put that in there to kind of point you in that direction. Okay, the next one we are just switching from logarithmic form to exponential form. So same concept, just going the other direction. The base of the logarithm is the base of the exponent. So this is 3 to the 4th. So base of the logarithm is the base of the exponent equals 81. Number 11, 3 to the negative 6 equals 1 over 729. And that should help us, or we should remember that a negative 6 exponent moves something to the denominator. Number 13, notice there's no base written, so that's an understood 10. So this is 10 to the negative 4 equals 1 over 10,000. Number 15, 0.1 cubed equals 0.001. And number 17, 1/4 to the 3rd equals 1 over 64. So that's changing from from logarithm form to exponential form. All right, the next section is just evaluating. So this is new to us. We haven't dealt with logarithms a real long time, obviously. So we're going to just evaluate some of these. So what we do here in our mind, I'll write out kind of what we think in our mind. We're trying to figure out, well, what does this equal? And we're a little more familiar with exponents, so we're actually thinking back in exponential form, 2 to what power gives us 256? So we want to find what's this. I think I've been telling you for a while now, it's good to know your powers of 2. 2 to the first is 2, 2 squared is 4. So you just keep doubling 8, 16, 32, 64, 128. Here's our number 256, 512, and 1024. So this is to the first, second, third, fourth, fifth, sixth, seventh, eighth. This is x has to equal 8 here. So again, in our mind, we're thinking 2 to what power gives me 256? So the answer is 8. So maybe thinking of through this 7 to what power gives us 343? Well, 7 squared is 49. 49 times 7 is 7 cubed, and that's 343. So our answer is 3. Okay, the next one, we're thinking 3 to what power gives us 1 over 27? Well, we know 3 cubed is 27, but we need 27 in the denominator, so our answer is -3. Number 25, that's a 10. So 10 to what power gives us 100,000? Well, that's, if we know our powers of 10, 100,000 has 5 zeros in it. So this is equal to 5. And I should have mentioned before, we can check all these because this would be like 10 to the 5th equals 100,000, which is correct. So 5 is definitely our answer. Number 27 actually reminds me of the one we went over earlier that I mentioned. Log base 6 of 6 equals 1. So this one here is equal to 1 because b to the first power equals b. And then this one, we're thinking, number 29, in our mind, we're thinking b, so we'll come up here, b to what power gives me b to the x? Well, what goes in that square right there? An x. So this equals x is our answer. So that's just thinking in terms of logarithms. We kind of mentally convert into exponential form. Number 31 just says use a calculator to evaluate each common log to the nearest 10,000th. So that's 4 decimal places. So you just pull out your calculator. Oh, I can't see it. So log of 6, well, that's log base 10 of 6 on your calculator. On the left side, you see an log, so I'm just doing log of 6 equals, that's 0.7782, because I'm rounding into the nearest 10,000th. Now part B, log of 60. 1.7782. It's interesting, that's the same thing there. Log of 600. Probably is going to have a relationship too. Log of 600, 2.77. So we jumped all the way to 200, but only jumped up 1 there. What about log of 0.06? Well, now we're going down some numbers. So log of 6/100ths. And that was -1.2218, which is related because 0.2218 and 0.7782 add up to equal 1, but that's not for now. And then our last few questions are graphing logarithms. So I already have some graphs drawn there, so if you need to take a minute to draw the graphs, well, you're supposed to be done this assignment already. Just as a reminder, to graph a log function, it's the inverse of an exponential function. So our x's and y's are switched, so our 3 important points are here. So we'll graph those first. Remember, b represents the base. So b is the base. 1 over b means the reciprocal of the base. And then also, I have this on here, there's a vertical asymptote at x equals 0, which is the y-axis. All right, so let's graph these points. So for number 35, we have the point 1, 0. 1, 0. We have the point B1, so 1, 0. The base 1, so 4, 1. And the reciprocal of the base, negative 1. So 1/4, negative 1. We know that the y-axis is a vertical asymptote, so we can use those 3 points. If you catch on to this stuff, there's also one at 16, 2, but that's way out there. So there is number 35. Now, the way this is set up, it looks like 39 is next, but it's not. Let's go all the way over to 37. We're going to graph our parent function. So this information right here is for the parent function. But then what happens when we add 2? Well, it's going to move up 2. So let's start just by graphing the parent function in red. So we have those 3 points. We have 1, 0. We have the base 1, and we have the reciprocal of the base, negative 1. And we know that the x-axis is, sorry, not the x-axis, the y-axis is an asymptote. So we have the point 1, 0. 2, 1. So it doesn't give me a whole lot. 1/2, negative 1. If you need to expand out more, you can realize it goes through 4, 2, and 3, 8. 8, 3. All right, so that is the parent function, but that's not what we're looking for right now. We need to add 2 to that. So let's go ahead and do this final answer in green. We did our parent function in red. This plus 2 is going to move everything up 2. So I'm going to take each point and move it up 2. I know these last 2 points weren't actually on our original 3 points. The asymptote doesn't change just because you move a vertical line. If you move a vertical line up 2, it's still just a vertical line. So there is the graph of log base 2 of x plus 2. Now we'll slide over to number 39, which is log base 4 of x plus 3. So what you want to do is graph your parent function first, and then it's going to move left 3 because we're adding 3 inside the logarithm. However, the nice thing is, so if we have this on a quiz or a test, you might have to graph log base 4 of x, but we don't need to do that because we've already done that. Although, you know what, let's go ahead and put those same points on here. So I'm changing my mind. We are going to graph this parent function. So we have the point 1, 0, 4, 1, and 1/4, negative 1. That's the parent function. And we're going to move everything left 3. So this one goes left 3. So it's at 1/4. It's going to go to negative 3/4, negative 1 1/4, negative 2 1/4. Sorry, negative 2 3/4. So that moves left 3. This one's easier. This moves left 3, and this one moves left 3. Our asymptote moves left 3, so instead of being at 0, it's going to be at negative 3. And so here is the graph of log base 4 of x plus 3.